Hello. Hello all. Can you hear me? Can one of you confirm?
Oh, yes,
Yes,
yes.
sir. Yes, sir.
Yes,
Yes,
sir.
audible.
Reading.
Okay, okay, sure.
Yes, sir, it is audible, but you be louder little bit?
Yeah, yeah, sure, sure. I'll try. Yes, whoever it is, please, you are requested not to switch on your audio or video without any purpose. Okay, so I will start. So as you know, the course name is Design and Simulation of RF Circuits. Okay, and I am Saurabh Roy. I am currently a fourth year PhD student in ISSC Bengaluru, that is Indian Institute of Science Bengaluru. And as you know, I am from India. So the thing is, as I know that some of you are from also abroad and all. So maybe you will have a, but given the large number of participants, it may not be possible to have an introduction. Uh, and it might not be possible to take questions from everyone. But as I see, you might be, added in the Teams group. So you can post your questions there in the Teams group, okay? And I will request others also to interact in the group, and you can also answer to others' questions. Okay, so that is the one part. And yeah, so before some of you are saying still not audible, I guess it might be problem in your side. You can try, logging out once and start, and log in once again. It might solve your problem. And given the design problem, so the fundamental parts are like we'll go through the basics of RF circuits quickly. And I am assuming that you know basic electromagnetics, including the transmission line section. Okay, that will be very vital for any RF circuit design. And as it was a prerequisite in the course, so I hope you know that part. And if you still don't know, and you might go through the Pozar book or any other electromagnetics book, and you can just revise that portion. Okay. I see still people are joining. So the thing is, given that is not a complete course, it's a short course, right? So I cannot cover all the small sections, derivations, all the nitty-gritties of the course circuit, right? So for that, you might have to go through the Pozar book and go through that. Okay. I will cover only the pinpointed theory which will be required for the design. All right. And I will be going through the ADS software, Advanced Design System, which is currently provided by Keysight. I will follow that and I will show you some of the designs. So currently the plan is Saturday there will be this time there will be a theory course or like small brief introduction to the concept, and Sunday I will show you some design, right? And then I will post a design problem for you. You are supposed to design that in a week of time. Okay, right? So initially it will be a very easy circuit like a coupler or power divider, which can be done within 1 2 days. So I will show you hands-on on ADS, and you might go through that and then do yourself, right? So if you do yourself, then only you will learn design. Otherwise, just by reading a book, you will never know a design. It's like, swimming by watching a YouTube video. Okay. So that is the plan. And so you should have a software like ADS or AWR or something like that. CST and HFSS you can use, but I don't know if you can, integrate some of the portions like amplifier and all. If you are okay with that, you can figure out, and it's fine. But I am currently not sure if you can do amplifier design and all those in CST or HFSS or not. So please find out ADS or AWR. There might be a student license available. You can, approach ADS software, or in internet only you can look into if there are free versions available like that. Okay, so before going into the theory, I will see if you have any question. Okay, please ask one by please raise your hand and then I will ask you. Yeah. Please raise your hand if you have any doubt or question. Okay, so first two people have doubt. One is Ajay Jadab. Yeah, Ajay, please.
Okay, so will this course include active circuit as well, apart from passive?
Yeah, right.
Like,
Yeah. You saw the course schedule, right? There is a amplifier section as well as a energy harvesting circuit. So for that, active circuit will be required.
okay, so and that amplifier is it power amplifier or just operational amplifier op amp, like analog one or RF one?
It's a RF design, right?
Okay,
So that
okay,
is why I told you, you go through the Fuzzer book, whatever you will find there, it will be basically that. So all of you, please go through the Fuzzer book
okay, okay.
and you will know that. Yeah. Next is Magan Tisa. Yeah, but the name is not Sede, only mail ID. Please ask.
Good afternoon, sir.
Yes, good afternoon.
Sir, apart from ADR or AW, apart from ADS or AW software, can I use multisim software, sir, for designing active and passive circuits?
See, the software is fine as long as you can design. I have no problem with the software. Okay. So if you can design, you feel like if you are okay with that, you are okay. You can do it, but you have to do it. I am not, I am not aware about that software. I only know about ADS and CST. Okay. So I can help you only in ADS. I will design myself and in ADS.
Sure, sure. I was unable to get ADS or AWS software, sir, so that's why.
Yeah, that is fine. As long as you can design yourself in any software, you can do it. Yeah,
Okay,
okay.
sir.
That part is
Thank you.
yours. You have to find out there. Yeah. Okay. So anybody else? Somebody? Ashok? Yeah. Yes. Ashok, you have a
Hello,
question?
hello,
Yes.
hello, hello. Good
Yes.
afternoon, Saurabh.
Yes. Tell me.
I want to know that's my query. Actually, I'm in Norway right now. That's like a time difference is scenario is there with me. I want to know there's a confirmed time on Sunday there as per in your flyer. That's like two times were mentioned there,
Yeah, right.
morning or evening, or
Hmm.
same on Saturday. There will be two times of class, or like there will be Saturday, Sunday. Like as per you are saying that theory part to Saturday and design part on the Sunday. I
No.
just want
No. Generally, yeah, we will cover only in the afternoon slot. Okay.
so Sunday will be afternoon, same time,
Both.
and Saturday will be same.
Yeah, both Saturday and Sunday afternoon will cover. And in case any requirements are there for tutorial and all extra tutorial, then we'll go to the morning slot. Okay. Otherwise,
Okay,
we'll
okay.
follow Saturday and Sunday the same time, 5:30 to 7:30.
Okay, thank you, yeah, thank you, sir.
Okay. Okay. Sure. And yeah, Dr. K.
Uh,
Saktis.
Sakti
Yes.
Sudan, myself. I
Yes.
Good evening, sir.
Good evening.
Could you provide me AWS software
No,
because we
sir,
are
no.
right now.
Yeah, see
Okay,
that part you have to do it, sir. I don't have any, access to any software. I have for myself. Okay, so that obviously I
okay,
cannot
sir.
provide to you. Yes. You can look into Google. There might be, free licenses or student licenses available. That you have to find out. Yes.
Yes. Thank you, gentlemen.
Yeah. Yes. And I see IUC. Yes.
Hi sir, so I want to know in case we miss any tutorial or something, so will
Mm-hmm.
recordings be available for all sessions in a drive or something so that we can repair it in future also?
Yeah, see the recordings. Currently, this is being recorded. Okay, so as long as this video will be over, you can see it, the recording in this Teams only. Okay.
Okay. So for all sessions we have to join through this link only.
Yeah. The same link every day. Okay. But the thing is, I will encourage all of you to follow the live class. Okay.
Uh-huh.
Yeah. So that you can ask question and it will be interactive.
Yeah. Okay. Thank you.
Okay. Okay. Yeah. Okay. Anyone else? Yes, Ganesh.
The power amplifier design will be
No, it
as
does not say power amplifier design. It's only amplifier design.
okay.
Tell me, continue. Yes. And okay.
Sir, one doubt
Uh,
actually.
hmm.
Means it's a normal amplifier means at what power level till what power level and what frequency we are able to
Uh,
design that.
see, sir. So, see, everybody, as I told you, this is RF design class, right? If you have seen my post in the Teams, it's not an analog course. So, definitely, I will not be going inside the amplifier. It's like what kind of MOS is there, how is the MOS configuration, not all that. So that's why all of you, I encourage you to, have the book DM Poser and go to that section of Poser book so that you will know basically what is there for RF design. So briefly, if you have a amplifier, okay, so amplifier is not about only amplifier. You need to have a matching section so that max power maximum power is delivered to the load, and as well as RF matching is there in high frequency, right? So in the RF circuit, one of the main approach is having a good matching as well as low power loss. Okay, so these things will be there, as well as another section is noise figure. Okay, so basically if you have a matching section added or some other network added, you might lose some kind of, you might reduce the noise. You can you can increase the noise there. So the thing is, you must have to have a trade-off there, like how much maximum amplification you can do, as well as how much and the noise figure also you have to minimize. So that is the thing. So we'll look into matching maximum power delivery or maximum amplification possible out of amplifier, as well as noise figure.
Okay, sir.
Yeah, so okay. And anybody, so who is this Mehemnet? You do not have to share anything. Why this is coming? Are you sharing your video? Okay. So now I will go into the video and I will start the lecture session. So I will request all of you to, don't switch on your audio or video unnecessarily, so that will interrupt. Okay. Okay. So I guess you will know, most people will know about the transmission line. I will start from microstrip line. Okay. So that will be covered in most of the circuits, because most of the circuits will design using microstrip line only. So I will start from the microstrip line section. All right. If you have anybody have any doubt or question, please raise your hand, or please speak also in between. Yeah. I might not see your hands there because I will be in the other slide, so I can see your hands. So feel free to ask questions. All right. Okay. Okay. So the thing is, if you see this slide, please confirm, only one guy, please confirm that you can see this planar transmission line slide. The
No, I
the
cannot
pic,
see the slides actually.
Yes,
yeah.
sir. Yes, sir. We are able to see.
Okay. So who is not able to see, please log out and log in again. Okay. Then you will be able to see. Okay. Okay. So the thing is, if you have seen any coaxial cable, you know there are two metallic sections. One is the inner conductor and there is the outer conductor. In between, you will have a dielectric, right? So that is actually Teflon. The dielectric is generally Teflon, and this and the wave will generally propagate inside this metal and through this dielectric. So that is one way to propagate TEM wave. And the other way, if you see, if you just cut one aperture of coaxial, it goes to the other section. It shows like a one metal and surrounding another metal. If you further make it flat, it gives you the microstrip line section. Okay, if you flatten a coaxial cable by pressing a force, you will see it's like a ground plane below, and there is an inner conductor, which is a microstrip line or metallic patch on top of the dielectric. All right. So this dielectric can be any substrate. What generally we see, like from FR4 to Rogers or Arlon, any kind of substrate. And there are other configurations possible like strip line where you have two ground sections and in between you have the metallic patch. And other configurations like like coplanar waveguide where you can have both the ground and metal or patch both on the same layer. Okay, and substrate is there. So now the question is, what is the advantage of microstrip line? Okay, and what kind of modes will propagate through this transmission line? Do they carry TEM wave? And what are the higher order modes available and how can we avoid it? So microstrip line, the main advantage is, as you know, it is a planar wave, right? So you can fabricate it very easily. That is one advantage. So it is very much possible to make a compact microstrip line or compact circuit on a substrate only. It will be a 2D. Okay. So before I start, one thing I must say. So these slides are provided by my professor or my advisor for my PhD, Professor KJ Binay from ISSC Bengaluru. Okay. So yeah, I'm grateful to him for the slides. Okay. So now going to microstrip line, let's see what are there. Okay, so you see the various configurations of microstrip line. There are inhomogeneity and homogeneity. So what is inhomogeneity? If you see in microstrip line, there are two substrates, right? So one substrate in definitely the normal substrate what you see, but there is also air because there is actually no boundary between the air and substrate. So they actually merge and they have a uh, common wave propagation. That's why it's inhomogeneous. And strip line or embedded differential lines and this kind of lines which has two grounded line is homogeneous because wave will propagate only through one kind of substrate or one kind of dielectric material, right? So we'll see what are the impact of this inhomogeneity in microstrip line. Okay, so these are the different substrates you might know, and it is easily available in internet and all. So you see RT5880 is a very good substrate, right? So that loss tangent is a great deal for design because it actually says like how much wave are you are going to lose there while propagation, right? That is the loss tangent actually means physically. So the lower the loss is better, right? So that is all there. Okay. Yeah. Now looking into microstrip line, you see microstrip is line is kind of a grounded slab. Grounded slab means there is a ground at the bottom, and on top of that you have a substrate. And on the top of substrate you have a very thin metallic patch. So how thin are these ground and metallic lines? Generally we take it as 18 microns to 35 microns. So generally people take these two. Okay. So 18 micron and 35 micron, you know, these are like around lambda by 100 or lambda by 1000, these orders according to your frequency range. Okay, so these are very thin lines. So the thickness will not matter actually at this range, but what mainly matters in the microstrip line design is the width of the line and the substrate height. Okay, and substrate permittivity. These are the design parameters. So three things are substrate height, substrate permittivity, as well as the thickness of metal patch. So if you see, so there are two main things in microstrip line or any other transmission line, like even in waveguide, that is TM line possible or not? TM mode possible or not? Okay, so I will ask some of you, like, can you answer that? Is it possible to have a TEM wave here? And why not? I will ask you, is it possible to have TEM wave in waveguide? Please raise your hand. Yeah, you can speak also. Yeah. And what is the criteria to have TEM wave in a transmission line? Yes. Anybody? Somebody said no. That is right. Okay. So I guess you can hear me, right? Hello?
Yes, yes, we
Yes,
can
sir.
hear you.
Okay, 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 right, right. Okay. Okay. So I am assuming you don't know. Okay. So only the one guy said he might know. So the reason is, so yeah, the reason is to have TEM wave, we basically need two metals, okay, or two lines. So why is that? If we have only one metal, like in a normal wave, rectangular waveguide or circular waveguide, it's not possible. Why? To propagate the wave or equivalently a current, okay, we need to have a forward path as well as a backward path. That is only possible when you have two lines or two metallic lines, right? So that is why you have in a coaxial line or microstrip line. Okay. But in waveguide, it's not possible because waveguide, if you see, is like only one metal surrounding a dielectric. So in that, the whole thing is having a same potential. So it's not possible to have a current going and coming backward. So that's why waveguide will not have TEM mode. It is only having either TE or TM. That is, and then they will, interact with each other and then they will propagate, right? Because the wave has to propagate. In which mode they will propagate will depend on the configuration. So now this T and TM mode are possible only in normal waveguide. But in two conductor lines, like our coaxial line or microstrip line, it is possible. Theoretically, it is possible. Now there is a problem in microstrip line that we will go into this, like why it is not perfectly TEM mode in microstrip. The thing is, if you see here, in microstrip, we have a boundary between the normal substrate permitted dielectric and the AR. Okay. This boundary between AR and the substrate is actually creating the problem. Why we can't have a pure TM mode. So the thing is, if you want to have a pure TM mode, is possible only when it propagates through only one substrate, only one dielectric. Whenever you have a boundary, in the boundary between these two mediums, there will be mismatch because there will be velocity of propagation different in two different dielectrics. So obviously it cannot sustain only one single mode. There will be two different modes in the and the boundary they converge. Okay, so there will be a mismatch. That is why it's called a quasi mode, quasi TEM mode. Basically, it is TE and TM mode together. So that's why you will see most of the time is like TM01 mode you will see, okay, in the microstrip antenna design, you see. But basically, because of the mismatch between these substrates, we will have a velocity difference, and that's why the phase, because the phase velocities are different, we will have a mismatch. Okay, so that's why basically the TEM mode and TE mode, both of them coexist in this configuration. If you see in this picture here, okay, both of them coexist. You see here, some portion is above the dielectric and some portion is through the dielectric. Okay, and the fringing modes, the fringing wave fields actually is caused because of this both TM and TE coexistence. But most of the fields will be inside the dielectric. Okay, and that's why this deviation from TEM is very small in comparatively lower frequencies, and that's why it's called quasi TEM mode. And that's why a very important parameter in microstrip line is effective permittivity. Okay. So whenever you have to design a microstrip line, you will be given some substrate, right? So from this substrate, let's say you have to calculate the wavelength and phase velocity and all this. So all this calculation will not be done through normal substrate dielectricity. You have to calculate the effective dielectricity. So you will have some tools in ADS that I will show you, and maybe in there are plenty of tools available in internet also. This website will show you what are the design things, and so the effective permittivity is you can substitute the normal dielectric as well as the air together as a combined dielectric with epsilon E. See, left is the actual substrate we have, and right is the substituted dielectric, which has a dielectricity of epsilon E. So this permittivity is given by the calculation is, you can find in the Poser book or any book. This is calculated through this. Okay. So it will have a thickness of D, and the combined permittivity will be calculated like that. So obviously, whenever you have to calculate the phase velocity or phase shift, you cannot take normal epsilon. Let's say you have a substrate like FR4. You cannot calculate a square root of 4.3 here. You have to calculate your epsilon effective from the permit substrate like FR4 or Rogers, and then you have to take that into account. Okay, this is a very important part for the design. And similarly, there are formulas for no, calculating line impedance like Z naught for the microstrip line. That will depend on the epsilon E as well as no, the characteristics of the line, like the thickness, and W is the width of the line. Okay, so these all are like mostly empirical formulas. You can find lot of tools in internet which will give you all these values. So you can note these two websites here, especially EM Talk and Everything RF and this EE Wave. There you can just put your values and you can calculate what would be the impedance as well as effective permittivity, all this. Okay. And also there is another website called Pasternak. They are also I generally use there also as well as EM Talk. Okay. They are very efficient. So you can go into this for, you can look into this for calculation, microstrip line calculation. Okay, so this is the first portion, introduction to microstrip line. Now I will go into the next section. So if you have any questions, please speak out. And anyway, the video will be available. You can look into later.
So do you mind mentioning the name of the book again?
It's DM Pojar, Microwave Engineering. Yes, Vignesh.
Hello. May I know what happens if the dielectric substance used inside the microstrip design, like air, how it impacts, like instead of some other substrate like FR4. So if air is there inside, will it impacts in any movement of the wave propagations or something, or is it is impossible to make a board inside having air as a
Okay, so
dielectric?
you are saying if we use air as a sub dielectric instead of some
Yeah.
FR4 or
Is
something.
it
Yeah,
really
yeah. So see, the advantage of air is, if you, I'll go into the slide. See, a dry air, basically loss tangent is 0 and epsilon r is 1. So obviously losses will be very low, and 1 is obviously, it gives you very good design. The problem with air is you cannot place the microstrip line or the thin metal on air, right? How can you put? So you need to have some substrate. The
Okay.
problem, you understand? Yes.
Yeah, it will be like a floating kind of thing,
Yeah,
like
exactly. You cannot keep it hanging like that. But there are things like, people use foam and this kind of metals, which is very close to air, but still is not a just a, air. It's not like a vacuum or something like that.
Okay,
Yeah.
okay.
Yeah.
So from this table, that which is closer to air,
I
any
see.
substrate?
No, here it is not given, but
Okay,
generally,
okay,
foam is close to air.
okay, okay.
Foam.
But there will be
Yeah.
some trade-off, right? Like if it is
Some trade.
close to
Yeah.
air, okay.
It will be around 1.5 or something, but
Uh-huh.
the losses will be there, some minute losses.
Mm-mm-mm. Okay.
Okay. Yeah. Anybody else? Yeah. Pernica. Yeah. Or yeah, this Aksat. Aksat. Yes.
Good evening, sir.
Yeah. Good evening. Yes.
Yeah, sir, does we calculate E effective only for microstrip line or something other?
Yeah, you can calculate for all other substrate. Wherever there is a inhomogeneity, like normal coplanar waveguide, and I will go to the slide once again. See, whenever there is a inhomogeneity, you need to calculate that because there is a boundary between two mediums, right? Here you see microstrip, CPW as well as differential line. All these lines has a boundary between normal substrate as well as epsilon naught, that is air.
If we sir put can we put sir two substrate together?
Yeah, you can put, yes. There is, there are a lot of microstrip line calculation with stacked substrate. So there also you will have effective substrate permittivity.
Okay.
Yeah, and next one is, okay, yeah. Please speak, Mahesh.
Yes, sir. Actually, when we are going for high power design,
Mhm.
means what should be the value of dielectric? Any idea? Dielectric and loss tangent means.
Yeah, obviously for very high power designs, you need to go to a very low tangent designs. Okay. So here if you see in this table, the LTCC is very more small, as well as you see Duroid 5880 very small. And nowadays there are a lot of designs in terahertz and all, which is done, integrated silicon designs, or some of them are in LTCC. So they will have very low loss. Okay. See SiO2 one chip here. This will have very less loss. Yes. Or gallium arsenide, indium phosphide, all this. Yeah.
So whenever we design, we select a substrate, it should have less loss tangent and less epsilon r.
Yeah. But see, the thing is not less epsilon r. Epsilon r, it can be big also. Okay, that will depend on how much confinement you want. See, generally, microstrip antenna design, you want smaller dielectricity, smaller epsilon. And for microstrip transmission line, you want higher transmission line. Okay, higher epsilon. Because the field will be more confined and the fringing loss will be less.
Okay, when we select epsilon r more means for transmission lines, generally epsilon r will be
M-
more and loss
More,
tangent will
more.
be less.
Yeah, right,
And where
right.
we are doing when we want to radiate means
Hmm.
epsilon r should be less.
Less. Yeah,
Okay,
so that fringing will be more.
okay,
Okay. Yeah.
okay. Good point. Okay, sir.
Mhm. Okay, so next is, yeah, we may take one more question. Okay, so then we'll move out. Yeah, so it may not be possible to take all questions. Somebody who is like Parnika.
Hi, am I audible?
Yeah.
Okay, I just wanted to ask, can you please comment on the width of the transmission line that's used for different dielectric constants being used? What's the relation exactly between the width of the transmission line and the dielectric constant of the material?
Yeah, right. See, the thing is, if you see the formulas here, the epsilon effective here depends on the W here, right? So that will be affected. More than that, the input impedance or the characteristic impedance of microstrip line Z naught is dependent on D by W ratio. So D is the substrate height and W is the thickness of microstrip line. So basically, let's say most of the cases we want a 50 ohm line, right? 50 ohm transmission line, and you are given a substrate like FR4. So you know the epsilon R, and then you have to design or fix your W such that the Z naught is 50. That is the calculation you have to do. For that you have to use these tools like these tools here, EM talk or everything. So you have a line calculation tool, and where you have to, let's say you have to make a 50 ohm line or 75 ohm line or 35 ohm line, and you have to calculate the W. Most of the cases, D, the thickness of the line is given, thickness of the substrate is like either zero point 0.5, zero point 0.8 millimeter or 1.6 millimeter. Okay.
Okay, thank you.
Yeah, sure. Okay, so I cannot take more questions. So you are welcome to post the questions, or maybe at the end I will take again. I will move to the next section. Okay. Okay, so the next section is, see, tomorrow my plan is to show you some design on the power divider or coupler, so that I will, go through some of the theories of that. So quickly, I will go into the scattering matrix. theory of scattering matrix, because it is one of the vital portions in any microwave design. We do everything in terms of, we analyze in terms of S parameter, that is scattering matrix. What is it? It's a matrix just like Z parameter matrix or ABCD matrix, which gives a ratio between V1 plus and V1 minus. What is this? So let's say this is a two port network, port 1 and port 2. In port 1 you have V1 plus and V1 minus, port 2 also similar. So what are these plus and minus? Whenever you put a high frequency line through a transmission line, some of it will be incident and some of it will be reflected. So that is this. So V1 plus is basically the incident wave and V1 minus is the reflected wave from that port. Okay, so this plus and minus, if you see here, plus tells us what is incoming wave and minus is what is outgoing wave or reflected wave. So that is why it is vital, because whenever there is a reflected wave, we know that the matching is not very good in that port. If it is very goodly, highly matched, then the complete power will, or complete wave will go into that port. Okay, there will be nothing coming back. So that's why S11 is vital. We want to measure how much incident and reflected power is there. So that ratio is here, you see, this is the S11. So what does it say? SIG. SIG is IJ at the two ports. Okay, so the notation is very important here. You see SIJ. So in the numerator, it is VI minus and denominator, it is VJ plus. So let's say SIJ is 21. S21 means at port 2 what you will get, given that at port 1 something is incident. Okay, so you see I and G chronology is very important. So 2 comes first, what I comes first is the reflected at that port and J is the second port, is the incident. So for S21 is what we will get reflected voltage at port 2, given that at port 1 what is the incident voltage. Okay, that is S21. So I guess you understand that. But there is another condition here. You see VK plus 0. That means all other ports other than this port 1 and 2 all must be having 0. That means all other ports must be matched. That is the condition of port S parameter. Okay. So again, let's say there are n number of ports. Okay. There are, let's say, 5 ports in a network. So in that port, in that network, S21 means if you incident S21 means if you give some voltage at port 21, sorry, if you give some voltage at port 1, what you will get at port 2? Okay, what is the reflected voltage you get at port 2? If your incident voltage is at port 1 and all the other ports in the network are matched, so then only you will get V plus equals 0. All right. So obviously, see, S11 is if you give some voltage at port 1 and at the same port, what is the reflected voltage, right? That is what we get as S11. So that tells us if we give some power at port 1, if all the wave is going inside the network or some power is also coming back, coming reflected from port 1. So that is what we want to stop. We want to stop the reflection. That's why we want to make S11, below minus 10 dB or minus 20 dB. So it is very close to 0. And S21 we want to maximize. Okay, so that whatever voltage we give at port 1, the whole power will be transmitted to port 2. That is S21. We want to maximize S21. Okay, so now the thing is, in the passive circuit, there will be S21 will be always less than 0. Okay, it will be, it will be always less than 1. So maximum it can be 1. Okay, but if there is a active circuit, like let's say amplifier or something, it can go even greater than 1. Okay, because you are amplifying the signal there using some other outside biasing voltage and all, so it can be amplified. But in a passive circuit, S21 will be always less than 1. So that's why reflected signal will be always less than 1. So there are some very important characteristics of S parameter matrix. So I will not go into derivation. So that says for a passive and lossless network, the conjugate summation are 1. Okay, so conjugate summation is 1, and if you take conjugate sum of a particular column with a same column, it will become 0. So the thing is, okay, so let's say it is a k cross k matrix. Okay, k cross k is parameter matrix. That means it has a k number of ports. So the condition or the characteristics of this S parameter matrix in case of lossless and passive is that if you multiply the same column or same row with the same column again and conjugate, the sum will be 1. Okay, sum will be 1. And if you multiply the conjugate to the another column, it will be 0. Okay, so that is what it says here, the condition. Okay, so these derivations and all you can easily find out in the book, Poser book. I will request you to go through that. But the main thing is, it may not be required that much, but it's just for any derivation. If you want to look, you may need it. So the thing is, you have to, because it's a matrix, it will have columns and rows, right? And it will be a symmetric matrix, by the way. Yeah, because it's a passive network. S21 or S12 will be symmetric. Okay, what you get at S port 2 given port 1 is S21 should be equals S12. That means if you give some signal at port 2, what you will get at S port 1. Okay, so that's why the matrix will be symmetric. So the thing is, X parameters we use in all the networks. Okay, and we basically characterize our circuits or antenna, whatever, how good or bad based on S parameter matrix. So see, this is a VNA, vector network analyzer. It is available in our lab. So you can basically measure the S parameters using the ports of the VNA, right? So you have to just connect your network with the VNA and you can see how much signal is getting reflected or transmitted through your port. Okay. Okay, so that is the basics of S parameter. And I will take some questions here before moving to the next section. Yeah, so yeah, please ask question if you have any question regarding this. Yeah, Mahesh, do you have question?
Yes, sir. Actually, there are Z parameters and other parameters, na, sir, Y parameters and all. So at
Right.
high frequencies, why specifically we have gone for S parameters?
Yeah,
Means,
if you see Z parameters is defined, how is it defined? You tell me.
yeah, it's voltages and currents, open
Currents,
circuit.
yes.
Yeah.
Yeah. At high frequency, can you define voltage and current at some point in a microstrip line?
Mm, no, I think we
No,
cannot
right?
measure practically.
Yeah,
Yeah.
exactly. So that is the reason. Because all these ABCD and Z and Y parameters are defined in terms of voltage and current. But in high frequency, the voltage and current becomes distributed across the line. Okay. So this is a very important point people generally often forget. In DC or low frequency, you have same voltage across the any metal, right? Anywhere you touch your multimeter or voltmeter, you will have the same potential. But if you see in a microstrip line or any other transmission line at high frequency, the signal becomes distributed. So within a small section will only the voltage will vary. So you cannot define a voltage or current at any point, or you cannot measure it actually, basically. Okay. So that's why we need to have a reflection based, transmission reflection based characterization.
Okay, sir.
Yeah. Vignesh? Yes.
Fine. The same question.
Okay.
Yeah.
Okay, sure. Next, anybody else? I see. I think some people. Yeah. So stick.
So one doubt, like as in the theoretically the formula it was shown that whenever I am measuring a particular S parameter, let's say S11, I'm assuming that all other ports are terminated or they're perfectly matched.
Matched, right?
But
Yes.
let's say let's say I'm measuring using a VNA and I'm calibrating it to some 50 ohms or something. So when it performs that measurement, does it actually ensure that all the reflection is constant and then it's zero, or
No, no.
like how is the
Yeah.
assumption?
See, yeah. So I don't know if you have done any measurement of a two-port or three-port circuit or not. Have you done any two-port measurement?
Yes, of like basic filters and passive components evaluation.
Yeah, exactly. So in that case, if you see, if you have to measure a two-port circuit S11 or S22, you have to basically, terminate the other port. Okay, with a load, matched impedance.
Yes.
Yeah, so that is where
But
you are
that
in.
usually yes, but that usually is a 50 ohm termination, right? And I do not know whether my filter is perfectly matched or not, because that parameter is
Okay.
given.
So yeah, so that's why while you design, there only you have to ensure that you make sure the ports are 50 ohm line. Okay, ports can be matched with 50 ohm line. That is what you do in design. You ensure that it will be matched to 50 ohm.
Understood. Okay. So that is basically an assumption that my the DUT is perfectly matched, and then I'm terminating, and then I'm measure like making the other
Exactly.
measurement.
Exactly.
Okay.
Yeah.
Okay. Thank you.
Yeah. Anybody else? And some people had question from the last section that also you can speak now. So we have some more time. We can go through that also. Yeah.
Do you manage parasitics when you go over high frequencies?
Sorry, in this section, I mean, see the microstrip line. Are you talking about microstrip line or what?
Yes, sir.
See the parasitics means, see, whenever you design, right? So if you characterize, you will have some parasitic capacitor inductor because of the fringing fields. So that's why we are not actually doing a lumped parameter calculation, right? We are doing a distributed calculation. So if you look into transmission line circuit theory, transmission line RF theory, you will see everything is a distributed parameter in terms of L and C and R, right? That is what it takes care of everything. Even the losses are being taken care of in the circuit transmission line theory, right?
But in practically, when you make a microstrip line board, so what are the care should be taken?
Yeah, so the practically whenever you do, the thing is you have to ensure that your loss tangent is less as usual, and you have to see the main thing. It comes when you go to very high frequencies. At very high frequencies, there it will not be close to TEM mode. There will be a lot of fringing happening, so you can't use it basically. Like people are talking about millimeter wave. Millimeter wave is still fine, but if you go to terahertz or like very high frequencies, 50 gigahertz and all, there it won't be useful as much in normal substrate. There the fringing will be very high and you can't. And the another consideration is, let's say you have to use a capacitor or inductor or lumped parameter in your circuit. Okay, so there you have to consider the parasitic elements there. You have to design taking care of all this, because in your the data sheet you get, that will come with lumped components as well as parasitics. You have to design taking care of all those. Okay.
Thank you.
Yeah. And next, Rebati. Yeah.
Good evening, sir.
Yes. Good evening.
Sir, what is the difference between of epsilon or with the highest value and lowest value? Is there any difference of taking this highest value and lowest, low value and high
Okay.
value?
See, as I told in the other question, I don't know you followed or not. So microstrip line you can use for antenna design as well as microstrip transmission line design. Okay. This section we are doing only transmission line design, but there are microstrip antenna also, right? So the thing is, these are very completely opposite things. Why? Antenna, we want it to radiate or transmit. That happens only when you have very high fringing. Okay. So to have that, you should have a very low epsilon r. Okay. When the epsilon r is low, that ensures the fringing is more, and the more and more wave will be transmitted towards the air. Okay. And when you want a normal microstrip transmission line, there we don't want fringing, right? Because we want the wave propagate through the board. If it fringe radiates in the air, obviously there will be a lot of loss. So there we generally want a higher epsilon value, higher epsilon R value. Okay.
So can I ask
Okay,
one
sir.
question?
Yeah, is it clear? Just a minute. Revati, is
Yeah.
it clear?
Yes, sir.
Okay, okay. And now, yeah, Mahesh.
Sir, what is the role of loss tangent? How to select it?
See, loss tangent basically, physically, it means it gives you more loss. Okay. So if you
Yeah,
know from definition wise, you know, right? You know, you have the
index.
Maxwell's
Yeah.
equation of curl H equals J plus J del D del T. So that is from that ratio you can calculate. But the actually, if you see, it is sigma over epsilon omega, right? So sigma, the more sigma is there, sigma by epsilon ratio, the loss will be more, right? So if you have a very pure dielectric, the losses will be less. But because you can get an ideal case, so there will be more and more losses. Okay. So
No, means
that,
for
yeah.
designing antenna and a transmission line, what value of
No, no.
loss
See,
tangent?
that's why I don't want you to go into antenna design now. The
Okay.
basically in the microstrip line section, microstrip transmission line design, you want to have a low loss. The loss
Okay.
is
Really?
should be loss in any ways, antenna or loss. It is like what is the loss happening within the microstrip line? That obviously you want to minimize, right?
Okay. Yes.
Yeah, yeah. Okay.
Okay. For any power, any frequency, anything, generally loss tangent should be less.
Yes, yes,
As per
yes. Loss should be less. Obviously,
okay.
if there is lot of loss in your circuit itself, then how it will not be propagated or radiated, right? Yeah.
Yes, yes.
Yeah,
Got it.
Uh, Sam, Suresh. Yeah. Yeah, Sam, are you speaking? I can't hear you actually. So Santosh has asked lot of questions, which okay, I can you speak, Santosh? So anyway, so the websites I have already shown you guys. I don't know, see these are the websites: emtalk, everythingrf.com, as well as pasternek.com. Okay, these websites are good, as well as all the commercial tools like CST, HFSS, ADS. They all have their own line calculation tools that you can use. Okay, for calculation.
Saurav?
Yeah.
Yeah, Sam here. So I
Okay,
just want
Sam.
to ask
Yeah,
about
Sam.
the,
You just one
yeah, I
minute.
just,
I am answering the answers of Santosh. So he also asked why 50 ohm and 70 ohm is only for termination in. See, the for historical reasons, you have to go to a standard, right? You cannot make all the things, all available homes possible. So, in all the available things like, our telecom standard, 5G and 4G, 3G, they all have a standard. So that is like that. In RF, people have decided 50 ohm and 70 ohms are standard. So what you get here, all the available terminations, whatever you buy from market, the terminations, the coaxial cables, all the lines, connectors. These are mostly made for 50 ohm, some are for 70 ohm. That's why when you go for a design, you have to either make for these 50 and 70. This is nothing, no hard and fast reason for that. It's just the no. This is the standard people have followed for a long time, and that is what you have to also follow. This is international kind of international standard it has become. Okay, and yeah, now Sam, yes.
Saurav, I just want to ask about the fringing effect in relation to epsilon R. I think
Okay, okay. Mm.
I think it is
Yeah.
like radiating to the air, right? The fringing effect.
Yeah. See here, if you see the field lines, the more the lesser the epsilon r, it will become closer to air. Yes, as you said. So the more it becomes closer to air, the fringe lines will be much more expanded, and that's why the fringing will be more and radiation will be happening there. If you look into microstrip line theory, there are two sections or two corners of the microstrip line, or the two corners of the microstrip patch will be actually radiating, and that happens because of this fringing field only.
Okay.
Yeah, and yeah, anybody else? Okay, so if not, we will go into the next topic. So now, given that you know about microstrip line, basic what is the microstrip line and what is S parameters, so those will be required. And I will, like, if you don't understand this, I will ask you please go through this, and obviously the normal transmission line theory. Okay. And one more important thing is Smith chart. I will ask you to have a Smith theory, read small read on Smith chart, because that will be used for design. Okay, it's very helpful tool in microwave. All I guess you all know about it, and it must be covered in your bachelor's or UG or whatever. Please go through it, and if you have any doubts, come back to me. Okay, so that will be required for us. Okay, so now I will go into the passive circuits. Okay, what are the main theory of passive circuits and how it is characterized. So the tomorrow I will show you some demo on power divider coupler, and you also have to design in the next week. Okay, I will give you a assignment here, and you have to try yourself hands-on so that you will learn. So let's go through the theory of dividers and couplers. What are these? So let's say we have a three-port network. Okay. So this, as you see in the drawing here, port 1, port 2, and port 3. Okay. Three ports. And let's say all these lines, all the ports are connected through 50 ohm line. So if you see, can you have a matching here? Matching means obviously port 1, there should not be any reflection. Now if you see at port 1, if you see from port 1, port 2 and port 3 both are connected parallelly. So two 50 ohm lines are connected parallelly. That means it offers 25 ohm at port 1, at the load of port 1, point P here. If you see here, my cursor here, point P. There is a junction of two ports, port 2 and port 3. It offers 25 ohm. So definitely port 1 cannot be matched. To match, it should have 50 ohm line. It should have a 50 ohm resistance there, right? So that means, simply connecting three 50 ohm lines together, you cannot have a matching. So how to do the power division or power coupling? Because often we need some circuits or networks which will divide, let's say phased array or similar circuits. You give some power and that has to be distributed among n number of ports. But if they in the junction, if they are not matched, so obviously there will be lot of power reflected back. So S11 will not be zero. That is what we want to minimize, right? That is the purpose of our design. We want to reduce the S11 and we want to maximize S21 also. That is one part. And another thing is isolation. What is isolation? So this port 2 and port 3, let's say we transmit or we insert power from port 1, and what we get at port 2 and port 3, if they are coupled together, so there will be a lot of crosstalk. So we want port 2 and port 3 should be very less crosstalk. That is what isolation means. So S23 or S32 should be very less. S23 is actually means isolation. If you give at port 2, if you if your input port is port 2, what you get at port 3 is port that is meant by S32. Okay, S32 again. S32 means from the notation. If you give input at port 2, what you get at port 3, that is S32. You want to reduce this isolation as much as possible. So obviously, to design this network, what are the things we want? We want all the three ports should be matched, right? First of all, we want all the three ports to be matched. So S11, S22, S33 should be as close to 0. And then we want S21 and S31 should be close to 3 dB. What is 3 dB now? If we want to use this as a power divider, we want whatever power we give at port 1 should be divided between power 2 and power 3 equally, right? In case of equal power divider. That's why 3 dB, 3 dB. In both cases, 3 dB means in the linear scale, it means half. 1 by 2 scales to 3 dB in log scale. So those are our design requirements, right? Now let's see how to make it happen. So what is the very common tool for impedance matching? If you have read the circuit theory or transmission line theory, you know very important section, one of the important sections are quarter wave line. Okay, quarter wave line for matching is used. So what is means quarter wave means in your design frequency, quarter wave or lambda by 4 section, microstrip line section you can add, which will and the impedance characteristics or character Z naught should be such that that section will match load to the input. Okay, so ideally you will know Z naught is given by Z in ZL square root of Z in and ZL. Okay, that is the design characteristics of quarter wave line. So please go through the transmission line theory, you will know it better. Otherwise, this is a very simple thing. If you have to match Z in input match to the ZL, a load impedance, you add a matching section lambda by 4 length in between, which should have a characteristic impedance Z naught equals to square root of Z in multiplied by ZL. Okay, so that is it. This is plain simple. So here the thing is, if you have to let's say match port 1 using a quarter wave section, so you can simply you can add see 25 into 50. Why 25 is because at the load section point P you have port 2 and 3 parallelly, 250 ohm parallelly means your load is ZL is 25 and your input you want 50 ohm, that is 25 50 ohm. So that's why your Z naught would be 25 into 50. So that means you have square root of 50 into 25 equals 35 ohm, close to 35 ohm. So that will make port 1 matched. But what about port 2 and port 3? Will it be matched? Let's see. Now let's see, look into that. So now the calculations, for the calculation, we'll look briefly into the calculations. We'll have a 3-column matrix for a 3-port network. And the diagonals will be 0 because S11, S22, S33 are 0. And this is symmetric. That's why S21 and S12 are 0. So that is at the third side, third rightmost matrix. Now if you calculate that for passive, lossless and reciprocal. See, these are the 3 conditions we are having now. Passive means obviously there is no active component here. Lossless means we don't want any loss. We are considering a lossless transmission line. And reciprocal means S12 is S21. Okay, because it's a passive circuit, generally it will be reciprocal. So if you calculate from this matrix, now you will have this 6 set of equations from here. Okay, if you calculate this, elaborate this matrix. Now, you see, to have this 0 equation solving, you should be having at least 2 of them should be 0. This calculation, if you actually expand, you will see yourself at least 2 of them, S21, S31 them should be 0. That means it's not feasible, right? S210 means if you are transmitting from port 1 to port 2, if you are getting 0, so obviously it will not work as a multi-port network. That means theoretically it tells us it is impossible to have a 3-port network. See, just note this 3-port network only. I'm not talking about a n-port or generalization. It is only for a 3-port network. You cannot have a passive that is also lossless and reciprocal and matching. All these things are not possible together. Okay, so that's why we have to add something here. Now let's see what is there. we can make it not reciprocal. How? We can add a component which is not reciprocal, like circulator, where Sij will not be Sji. If you see circulator, you add a ferrite material which is not a linear material, it's a non-linear characteristics. So then it will not be reciprocal. Okay, that is one solution. Another solution is you can add the network to be lossy. Okay, lossy means you can make some element there which creates some loss. That is one solution. Or you can make an active network. That is another solution. So now what is a easy solution? Definitely circulator is not easy solution. The ferrites will make it, it will not be anymore a 2D circuit, okay, planar circuit. So for that, we will go for a lossy circuit. Okay. So now for a 3-port network, how to make it a lossy? See, that's why it comes Wilkinson power divider. The concept of Wilkinson power divider is you add simple resistance which is lossy element, then it makes a 3-port network which is matched as well as passive. Okay, 3-port network with all the ports matched, and it will be as well as passive. Okay, this is called Wilkinson power divider. Power divider, why? Because if you give power from port 1, you will get port 2 and port 3 divided. Same power will be divided into it. It's called Wilkinson power divider. And you add a resistance in between this port 2 and 3 as the design. Okay, so now if you see theoretically how it is solved, if you just look into this, the right side here, picture here, I don't know if you can see my cursor or not. So if you add 2 quarter wave section lines here of square root 2 Z0, the impedance will be square root 2 into Z0. Then input impedance, what you see here, will be 2 Z0. If you see into the theory of quarter wave line section, input impedance is given by Z in equals Z0 square by ZL. So Z0 square is root 2 Z0 here. So definitely you will have the junction of port 2 and port 3 as 2 Z0. Both will provide 2 Z0 parallelly. That will give a impedance of Z0. That is how port 1 is matched. But as you see, if you look into port 2 and port 3, if you calculate like that, you will find they are not matched. Okay, so that is why we bring in the resistance here. Okay, now we'll see the analysis, how it is analyzed, and we'll see how we see that port 2 and 3 are also matched when we bring in the lossy resistance here. Okay, so before going into analysis, do you have any question? Yeah, please speak if you have a question. Yes, Bhigne. Vignesh, yes. Yeah, anybody, any question? Yeah, speak.
Yeah. Just regarding that quarter wave line. So is it applicable for both the lower source impedance and the higher source impedance with respect to the load impedance? Like for example, if our source impedance is like 20 ohm and the load is 70, and it's vice versa. So the quarter wave helps to match both the end if it is lower or higher. Will
Exactly. Yes. That is the theory of quarter wave line. You can match both ways. Yes.
Okay, fine.
Yeah, but only if you look into the theory, the constraint is both the input impedance as well as load impedance should be real. It cannot be complex line.
Okay.
Yes.
Yeah. Noted. Thanks.
Yes. Anybody else?
Good evening. Am I audible?
Yes. Sasi, yes, speak.
Yeah. The thing is here, suppose, for example, I'm designing a quarter wave transformer for matching at, say, 100 megahertz frequency.
Right.
Okay, the wavelength is coming approximately like 3 meters.
Right.
2.99 meters it will come. Okay. So quarter wave, if I take, it is almost like 0.75 meters.
Right.
So when I implement such a say for example the power divider or a coupler with these dimensions, I think it is not going to be a viable solution because the size of the circuits will become very bigger.
Yeah, that is, see, that's why we have moved on to higher frequency, right? That's why we don't use circuits in
But
100
still we
megs.
have certain applications where actually the lower frequencies we are using, isn't it?
You are using, yeah, right, yes, right.
Because for micro this like satellite communication, all these links. Suppose if you take 400 megahertz, these frequencies still people are using.
Okay.
Okay.
Yeah,
So in
see,
that cases,
400, if you look into 400 megahertz again, so then it will be like 1/4 of what you are saying, right? So still, then again, it becomes lesser. Yeah.
no, but 400 it doesn't make much difference. No, still you will have a huge length.
Ah, the see,
Okay, it's
it's
almost
You
like
can
a
use this meandering line type, something like that. Meander.
see, the thing is, you are saying whatever. The thing is, it is not a constraint of the microstrip line or quarter wave line, right? It is the design of high frequency itself. So whatever you design, it will be in terms of lambda, right? Wavelength will be proportional. The dimensions will be proportional to lambda.
correct.
So that is a constraint we have, right, in the lower frequencies.
Yeah,
Yes.
yeah. So that is where actually I'm thinking whether any alternatives could be brought there, like a mixed mode
Uh,
transmission line.
no, sir, no, that is not possible. But yes, what I think Rajendra said, that is sometimes you have to do a very big line on a small microstreamline
Correct.
section. People do use the meander line section so that you can make it compact. Yes.
Yeah, and one more question here. The thing is, like, suppose, say, for example, if I'm using a FAR4 substrate on which I have to print my divider,
Yes.
so its epsilon r is going to be 4.4. Okay.
Right.
So now the question comes here, as the width, as the impedance goes. Say, suppose if I'm dividing a 50 ohm into two ports, it will give you 100 ohm, 100 ohm. That is a
Yeah,
splitting.
right.
Further, if I split that 100 ohm, it will become 200 ohm, 200 ohm.
Right.
Further, if I split that 200 ohm into two, it will become 400 and 400. It will go, keep on going the impedance, isn't it?
Yeah, right.
The impedance values, as the impedance value increases, when you look at the Z0 equation that what you have showed,
Right.
okay, there is a dependency of width and thickness.
Right. Yes.
Correct. And if you look at that, as the impedance increases, the width will become lesser. That is, they are inversely proportional.
Right. Yes. Tactically, it will
Correct.
be very thin. Yeah.
Yeah,
Right.
it is very thin line actually. As your impedance increases, it will become more impractical. Like we cannot implement at some point of time. Maybe I'm not sure because it may
Yeah.
come around
Yeah. You see,
point zero 0.01 millimeter or point 0.001
right.
millimeter.
Right.
And solutions
So the
we have.
solution is okay. Continue. Yes.
Yeah, I'm just asking, is there any solution? Suppose if you encounter such a situation.
Yeah, right. So the thing is, in that case, you obviously cannot use a simple circuit like that. Okay, you cannot just stack 8 Wilkinson divider like that. So there are solutions there where you have 1 to 10 divider. Okay, there are dividers like multi-port Wilkinson divider. You can look into that, and there are like Geisel power divider where you have only one input and it will give you 8 number of output ports or 10 number of output ports. Okay, you can look into that in port divider. That theory is also there. Okay, in port
And
divider.
one small question. This already see. Ultimately, we have like a standard. You mentioned 50 ohm or 70 ohm connectors. They are available. Ultimately, the source should be 50 ohm.
50
So
ohm,
if I
right.
divide 50 into 10, if I divide 2, it will become 50 by 2. Sorry, 50 into 2. If I divide into 10 ports, it will become 10 into 50.
No, that's why. See, there the theory will not be as simple as like that. It will not be straightforward divided. Yeah. That's why the circuit will get complicated and all. So I will like suggest you look into this, multi-port network. Okay.
Okay.
Yeah. So that is what the challenges in design. You have to design such a way that it will still become feasible, right?
Correct.
Yeah. Right. But is there? You can look into especially in multi-port Wilkinson divider as well as Geisel power divider, GYSEL. That also you can look into. Yeah. Okay. Next, Ashok.
Yes. Saurav, I want to know just like because we are just talking about the power divider or something like my question is that if we connect like there's a one strip line is there and we connect both side of the source like port one and port two on the same strip like then both side we are applying 50 ohm impedance. What is the impedance of this total line at this condition?
What is the impedance at what? Where did you see?
Like basically there's a like line I'm connecting or like on the simple patch antenna or there's like a and there's a simple total cover line and port one is another side and port one is the same
Port two.
side like
Yes,
both
yes,
are
yes,
connected.
yes.
What
Right,
is
right.
the impedance of the line at that condition?
Okay. See, so you are saying at port 2 you are connecting some load and you have a some length microstrip line. What should be the impedance you see at port 1, right?
Yes. Yeah.
See, that's why I don't know if you are familiar with transmission line theory or not. Did you read transmission line theory?
Yeah, exactly. I read some. Yes.
Yeah. So if you see there is a formula for a length of L transmission line. What should be the Zn? Given a load at ZL, what should be the input impedance of transmission line Zin, where the length of the line is L. So there is a formula which is generally connected to tan beta L, tangential electrical length, and the input impedance is connected to load impedance as well as the characteristic impedance of the line. Okay, it generally is a complex equation. Okay, you please look into that, then you will understand. It's a very simple and well-known equation.
Okay, actually, in like you are saying about that, like if we are connected to that's like a impedance will be half or something. I'm
No,
just like
it's
asking
not a straightforward
just
equation
it
like
will
that.
not just half like that. Yeah.
No, it's not a half. It's a complex equation. It will give you J tan beta L. J is the complex value, and tan beta L will depend on the beta and L, and Z naught and ZL will be there in the equation as well. Okay. Yeah.
Okay.
Please look into the transmission line theory once, and you will understand easily.
Okay. Thank you, sir.
Yes. Anybody else? Yes. Okay, so then otherwise I will go into the next section of the line. So how to analyze it mathematically? Like let's say 3-port power divider. We have understood with some intuition that is not possible without any lossy element or non-linear element. Okay. So now in the Wilkinson power divider, the concept is you add a resistance here, and let's see how theoretically you can analyze conceptually, mathematically, this kind of lines. So the theory here, it is, you can divide the lines with two different configuration, which is called odd even configuration. Okay, let's see. So odd even configuration is a very unique theory people have, and very simple also. Okay, so odd even means if you have a symmetry in your line, you just cut the line in between. Okay, make it two different sections, and where you give once a symmetric source and once anti-symmetric source. Okay, that is it. See, thing is, you see here, there is a 4-port line as well as a 3-port line. Now, all the lines, wherever it is, a symmetric plane is there. That means if you have a mirror here in between the line, you can have a mirror symmetry on the upper and lower section. There you can use this even odd mode analysis. And how you do it in the odd mode? Let's go to let's see how we use it for our Wilkinson divider 3-port network. Here you see we divide the line here. How do we divide the line? Here we have a resistance in between, right? We have to cut the resistance so that some section goes to the upper half and the other section goes to the lower half. So that is what we are doing. So how do we do this R here? You see, we divide as R by 2 and R by 2. Okay, it's very simple, you see, but so simple and very unique thing. You just divide the resistance as 2R by 2 resistance in series. So then you can cut in between. You can make it symmetric, right? Top and bottom. Similarly, at port 1 load, we have Z naught. right? This Z naught we divide by Z naught and Z naught, two Z naught in parallel. Two Z naught impedance line parallel or two Z naught load in parallel gives you Z naught, right? So that is how we are dividing it, this network. And then in between we put a mirror and we divide it. We cut the line in between. Then if we cut it, there will be some floating section, right? For how do we address that floating section? Yeah, there it comes. Even more means V, see the port 2 1 and port 2, we are giving applying some voltage VG1 and VG2 here. If you see in the picture, the bottom picture, we have VG1 and VG2 here. Okay. So it says an even mode, you have to apply both of them same voltage. So now see, if you apply same voltage in the both section, so definitely there will be no current flow through the resistance here because they are in same voltage node, right? Same voltage. So basically they will be open circuited. There is no current flow through the resistance, so they will be open circuit. If you cut them in between, you can take both this R/2 as open circuit in even mode. Now look into the odd mode. Odd mode said this VG1 and VG2 you connected with defined voltage, opposite polarity voltages, +1 and -1, let's say. There what happens, because you have the +1 and -1 across the resistances, opposite polarity voltages across the resistance. So in the middle, obviously it will be grounded or shorted, right? So plus V and minus V, in between is what? Zero voltage. So that's why in the odd mode, if you cut in between the circuit, you will have these resistances shorted. The same happen in port 1 also. Okay. Now, if it is clear, now we'll go into the circuit with cut portions. Top half cut, bottom half cut for two cases, even mode and odd mode. So now the question comes.
Sir,
Yeah,
can you
yeah.
explain the second odd mode one?
Yeah, so yes. Odd mode says, if you see here, the clearly it says VG1 equals minus VG2. Here VG1 at port 2 and port 3, what you give, it provides the same voltage but opposite polarity, plus V and minus V voltage. Understand? If you do that, then what happens? Across this resistance here, you have two different voltages. So obviously in between will be what? Zero voltage, right? If you have plus voltage, +5 and -5 across some current element or some voltage, some network, in between it will be zero or it will be grounded. Obviously, because current is flowing from +5 to -5. There has to be zero voltage in the middle, right? Because it's symmetric also. Understand? That's why we short it in between. Is it
Okay,
clear?
got it. Yeah, clear.
Yeah, exactly. So now that is how we divide the network. We cut it and then analyze it. And while cutting this R/2, these resistances we cannot keep floating, right? Wherever we cut, those sections has to be either opened in case of here open circuit in case of even mode and shortened or sorted in case of odd mode. That is how we do. Now the question is why we do all this. Basically, we want to analyze this parameter. What should be the S parameter network? Mathematically, we want to find. In for this case of Wilkinson power divider. Okay, we'll see now. Look into the further slides how it is happening. See now you see the top portion in the even mode analysis. See R/2 is open circuit here in the near port 1 and 2 junction here. We have a quarter wave line section Z here, which is λ/4. Okay, we will look into what should be the Z value, impedance, characteristic impedance value. And again, V1 port is open circuited. Why? You see here also you have divided. Port 1 also you have divided, right? And the interesting thing is, if you see, we have taken value of 1 of all the resistances. R. This is generally normalized. Generally, microstrip line calculation, we normalize with Z0. What should be the Z0 is generally 50 ohm. So that's why we take 1 means it's a Z0 value 50 ohm and 2 RZ R means RZ0. 2 means 2Z0 100 ohm. See here 2 comes because 1 we have divided parallelly between 2 and 2. So that's why 2 means 2Z0. It has been normalized. See, that's why here you see here. Now the top section of the Wilkinson power divider, we have one at the section of port 2 connection because it will be terminated with Z naught. R by 2 is open circuited, which is the connecting resistance between two ports, port 2 and port 3. And at port 1 also it is open circuited. So now the thing is, if you see what happens here, the termination impedance of port 2, if you have to match, right? So at port 1 here, I mean at port 2 here, where VG equals 2 voltage connected, you have to make 50 ohm, right? 50 ohm only means matching. If you need 50 ohm matching, now for a quarter wavelength line, L equals lambda by 4, the Z naught has to be input and output, right? As I told you, for quarter wave line, at the output of this microstrip lambda by 4 line is what? 2. 2 is connected here, 2 Z naught. And input we want 50 ohm line. So obviously the characteristic impedance will be square root of Z in into ZL. That is why it becomes root 2 Z naught. That's why it is taken as root 2. So that is how we calculate that Wilkinson power divider. You will see here will have a quarter wavelength section of characteristic impedance root 2 Z naught. This is clear from this calculation. Is it clear for you guys? Yes. Otherwise you can ask question. So from this even mode calculation only, we understand what should be the characteristic line of the line we have added in between port 2 and port 1. It says from the simple quarter wave line theory, if you connect a root 2 Z naught line, it will give you a matching. Okay, so now next we will go into the odd mode analysis. See, odd mode analysis, I told you, if you connect opposite polarity voltages, you have to shorten it. The R by 2 is sorted as well as port 1, that is also sorted. Now if you see at the port 1 end, if you have shortened, that's why through this 2 Z naught load resistance at port 1, that there will be no current flow because before on there only you have sorted it. Now at port 1, at port 2 end, you have R by 2 sorted to ground and there is some transmission line sorted to ground. So transmission line, if you know lambda by 4 line, if you short at one side, at the other side you what you get is open circuit. It's very clear. Transmission line says, theory says, if you have a lambda by 4 line, whatever you connect at the other side, load side, will be opposite in the other side. So that means if you connect to a open circuit, you will get a short circuit at the input side or vice versa. If you connect a short circuit at the load, you will get an open circuit in the input side. So that's why this lambda by 4 line will not be useful at all because it will give you open circuit here at V2 point, voltage V2 here. Here you see a open circuit due to the lambda by 4 line. So there will not be any current flow through that. So only for the calculation, what is left is R by 2. R by 2 is sorted to ground. So basically whole current will flow through this resistance. So now it means, see, R by 2 is connected to a 50 ohm line at port 2. It has to match. So R by 2 has to be 50 ohm, right? It's as simple as that. So fundamentally, from this odd mode analysis, we see that for port 2, we have a R by 2 load connected. So obviously to look connect, matching R by 2 has to be 50 ohm. That gives R by 2 is 100. Or if you normalize it by 50 means R equals 2. So that is how from even mode and odd mode analysis, we get that Wilkinson power divider. First one is what should be the length and the characteristic impedance is root 2 Z naught and the resistance value is 2 Z naught. So these are the two basic characteristics of the Wilkinson power divider. One is the matching section you add in between port 2 and 3 and 1. this matching section has a characteristic impedance of root 2 Z naught. That is how we get what we get from the even mode analysis. Okay, this is this. And the odd mode analysis tells us the resistance in between them in port 2 and 3, which is isolating port 2 and 3, has a value of 2 Z naught, that is 100 ohm. This is as plain as that. Not only that, even further you can go and even calculate the S parameter itself. That I will leave you for yours, because transmission line, it requires much more transmission line theory. So you can basically take voltage of e to the power j minus beta x and gamma beta x. Then you can calculate very plain simply here what should be the voltage at port 1 and port 2. Okay, for even mode and odd mode. If you get both of them, then you can actually superimpose what will happen if you add both of them. So basically, then you get S12. What is the S12 or S21? It says what you get at port 21, what is the voltage at port 21, given your input is at port 1. So you have to add even and odd mode because it will be superimposed. Okay. So with this theory, is so powerful and but very simple. You can actually calculate S parameter as well. Okay. So it shows, see, this is the S parameter matrix here. If you calculate through this, you get S11, S22, S33 is 0, all 0. S21 and S31 is 1 by root 2, 1 by root 2. That means 1 by root 2 means what? Means power is getting divided into half and half. 1 by root 2 square is 1 by 2 in power. So basically you get half power, 3 dB power going into port 2 and port 3. And why J is there? J means there is a phase shift of pi by 2 because it's a lambda by 4 line. So there will be a phase shift of pi by 2. Okay. So that is the theory. You can, intuition and also you can from through basic intuition, you can understand what will be happening. If you give from port 1, what should be there port 2 and 3? There will be phase shift as well, right? As well as amplitude shift because of power division. So yeah, this is the analysis of Wilkinson power divider. And this is, it might be as old as I guess 50, 60-year-old theory, but it's still very much useful. You can definitely build up on it and make it much more useful, much more complex network. But in this very plain form, you see is like just adding a normal impedance and quarter wave line, how you can make very simple and useful circuits. You can make a power divider into half power, half power. Okay. See here it says like it was introduced in 1960s for coaxial lines. Okay, it is as old as that, around 64 years old. And there are other extensions available for unequal power division. Okay, so those are also available. You can look into that. But basically, we will show you tomorrow this design. And okay, so before going to a 4-port network, I will see if you have any more questions on this. Yeah, please ask any question on this section.
Sir, will you cover resistive power divider also?
Resistive, no. See, resistive you can do is as simple like this only. But basically, we want to focus on microstrip line based circuits, right?
Okay.
Yeah. But the concept is same. You can, even divide even and odd mode there also. Yeah.
Sir, actually, if we want to design a power divider for broad range, like 1 to 10 gigahertz, so can you explain that also in future? Means you may design only for one particular frequency, right?
Frequency, yes. Yeah.
But
See, yeah, that may not be possible in this short course, right? You have to look into much more, sophisticated things and all. So that you have to do yourself, We can in this short course cover only specific section.
or you can share some material related to some Excel file will be there, na, sir? Number of orders of lambda by 4 sections.
So you can use a tapered line or exponentially tapered section line. Those are all available for broadband, right? Yes, that you can do. Even what people use is that, the waveguides are very good broadband circuits, right? And the uh, much more sophisticated waveguide lines today is SIW lines. People can use that also. You can look into that SIW based circuits. Okay, they will be very
That
broadband.
means that is like can be fabricated, sir, or
Yes,
waveguides, no?
yes.
It can be fabricated on PCB.
PCB, yes, that's why these SIW circuits are very brilliant. You can look into that.
Okay.
Okay.
They also follow this microstrip. Means material may change, but concept is same. Or
concept is similar to waveguides. See, SIW means substrate integrated waveguide. Okay.
Okay.
So it is basically a waveguide made into a substrate 2D design.
Okay.
It follows closely rectangular waveguide theory.
Okay.
You look into that, please.
Yeah, sure. Thank you.
The power is scalable.
Sorry.
The power divider can be scalable of different powers.
Yes. There is possibility. Yes, there are a lot of designs of unequal power divider, and n number of ports are also available. Yes. As I told you, this is like 60 years old circuit. So definitely in 60 years there has been at least 60 versions of it. So you are welcome to look into Google Scholar. Generally, I search from Google Scholar for the recent work on it. Okay. Okay, so I'll go into quickly into 4-port networks also. Yeah, so now that 3-port circuits are there, we'll also look into 4-port networks. See, there are very useful circuits because you can have power divider as well as power coupler both together. And there are other things also. You will have a very good isolation between the ports. And you need not have any lossy element there. There's the factor. In 3-port network, you have to connect a lossy element uh, just to get that all the things available. But 4-port network, if you see a network like this, theoretically it says it is possible to have a matched at all the ports, lossless and reciprocal. All these things are possible in a 4-port network without any lossy element, without any nonlinear element. Theoretically, it was proved. So that's why this is also called a directional coupler. Okay, you will actually have in one direction some amount of power going, but in the other direction almost no power going or some other power coming. So it has some directivity in the network. That's why it's called directional coupler. Okay. Some very important couplers are branch line coupler, which is also called quadrature or 180-degree hybrid coupler. Okay, you see in the left side picture here, this is called branch line or quadrature coupler. And then we have a ring coupler or rat race coupler, which is also a very good important circuit. And another is coupled line coupler. Okay, that is also excellent. So basically, the quadrature and rat race is very widely used in all the microwave circuitry, but it is very plain and useful, and you can easily fabricate them on microstrip line. So please look into this, the theory, if you want more in-depth analysis of mathematical part like odd even analysis, which is done in the Posar book itself. But if you do actually, you will find a S parameter matrix like this. Okay, for a quadrature line. So quadrature line, you can actually do the analysis and find out this. It has 4 ports of the network. The in between lines are all lambda by 4 section, and the characteristic impedance is Z0 by root 2. That means it is around 35 ohm for a 50 ohm line. So if you do like fabrication like that, see, you see the port 1, 2, 3, 4, 4 ports, right? If you give power from port 1, port 2 and 3, it will be equally divided, but port 4 you will receive almost zero power. So that's why it is completely isolated. Port 1 and 4 are isolated, and port 2 and 3 are equally power divided. So similar things happen if you give power from any other port. It will be completely passive and reciprocal. That is the beauty of this circuit. You have port 1 and 4 completely isolated, but power is getting propagating to port 2 and 3 only. Okay. So that also you see from the, the matrix here. So if you see here, the S11 is 0 as usual. S21 is J by root 2. That means, there will be a lambda by 4 phase difference and you get half power. S31 you get lambda phase difference, sorry, lambda by 2 or pi phase difference, and 1 by root 2 power is getting divided between port 2 and 3, but there is phase difference between two. What is the phase difference? That is again pi by 2 or 90 degree, because there is a lambda by 4 line in between port 2 and 3, right? So if you see S21 and S31, you will get almost like same power, but there will be a 90-degree phase shift between them. All right. And S41 is all again 0 because they are isolated power. So similarly, another design for a 4-port network is rat race. In the rat race is just a, circular design, and the name is very funny though, rat race. Although I don't know if any rat was racing around this or not. But the characteristic impedance, if you calculate through the odd even mode again, it comes out to be square root 2 z naught of this circular line. Square root 2 z naught. And the line lengths are very, uniquely designed. There will be lambda by 4 between two, lambda by 4 gap between all the successive ports. So if you see lambda by 4 in transmission line, it gives you actually 180-degree phase shift. Okay. So 180-degree phase shift means in some port you will have a uh, the additive interference, and some port you will be completely deductive. So somewhere it will get added up and somehow it becomes 0 because of 180-degree phase shift happening. Okay, so that is the basic theory between this. And but the S parameter matrix is quite similar if you see. Okay, if you give power from, port 1, so if you see port 2 and port 3, again you get half power in both cases, and port 4 is again isolated. Okay, so that is the theory. So again, if you give power from one port, port 2 and 3, it will be like isolated, and port 2 and 3, it will be equal power division, and there will be some phase shift between them. But port 4 will be again become 0. That is one part. And there is another advantage of this thing. This is like power division, right? But it also works as a power coupler. Like, let's say this port 2 and 3, if you see, if you give power between them, port 2 and 3 in the rat race coupler here, port 1 will be added up in same phase. And in port 4, it will be added up in differential phase. So basically, if you give same power in port 2 and 3, you will get in port 1, you will get as port 1 will be 2 plus 3, P2 plus P3, and port 4 you will get P2 minus P3. So you will have a sum and difference, okay, between the powers. So you will have in the same network, you can do a power division, power addition, as well as power subtraction. This is called power coupler. Okay, that's why it's called coupler. You are coupling two powers from two different ports. So in the power divider you saw, it could divide the power. But here you see, you can divide the power as well as couple the power. Both ways it works. Okay, that's why this is, but these are passive also. It's very brilliant circuits, and very simple networks, but it still works maybe after 100 years. Yeah. So that is the basic theory of the this network. Yeah. So yeah, this is for today, and tomorrow we'll see the design. Okay. And do you have question here?
This is applicable only for microstrip lines or even for the amplifiers?
Yeah, amplifiers means amplifier. I didn't understand.
No. This power divider and coupler. Suppose if I have a class A amplifier of 300 watts, so can I add the two powers?
Yes. See, in any
Or
RF
dividing
circuit,
the power?
Yeah, it will work. Yeah, any power divider coupler, it does not have any. It does not have to do what source you provide. You any source you give from your amplifier or direct power source from somewhere, it does not matter. It will divide nonetheless. Yes.
So what will be the losses?
The losses, yeah, the losses will be 3 dB, right? That is what I'm saying here. You see the S parameter here. S parameter shows what? 1 by root 2. 1 by root 2 is If you take 1 by root 2 in the log scale, it means 3 dB. Because it's dividing the power, right? If you give power at port 1, port 2 and port 3 to port 2 and 4 here, it will be divided. In the case of rat trace here, if you give power at port 1, port 2 and port 3, power will be divided. Divided means same power, 3 dB, 3 dB. So that is the loss, 3 dB loss you will have if you take it as a loss. Otherwise, if you have a very good lossless transmission line, there will not be any extra loss there.
Okay, I don't know whether I'm asking a crazy question. So how you quantify the efficiency?
Efficiency, see the it will depend on the loss again. Efficiency we generally take for the active circuits only, right? Because there is a function of loss and all. Because we are having a passive circuit and we are assuming it's a lossless transmission line, so generally that efficiency factor will not be coming here. Okay. So we'll see the efficiency will come when we do a energy harvesting circuit as well as amplifier. There only it comes.
Thank you.
Yeah. So I will like if you want to know much more about theory and all, I will suggest you please go through the book once again, DM Pojar. It will be much more clear. But see, because short course, I cannot go much more in depth. It's not just possible. Okay. So I'll go theory as much as possible in one class, and the next class I will show you some demo. So if you don't have any more questions, we'll meet tomorrow afternoon. Okay, same time. If you have questions, you can post in the Teams. Please don't mail me and or links, message me in LinkedIn. That I may not be able to answer those. Post the questions in the here Teams only. Yeah, and also I will suggest you guys to have discussion in the Teams so that any other guys also can answer your questions. Yeah. And any suggestion is also okay. Yeah.
Sir, will you provide slide and the recorded lecture?
No, slide will not be provided, but the recorded lectures are there. You can, being a member of the team only, you can look into that. Okay.
Okay, sir.
Yeah. So instead of slide, because mostly the slides are taken from the book only, this Pojar book, I'll suggest you go through the book itself. Okay. And whenever required, I will post some papers or something so that you can go through it. Yeah.
Okay, sir.
Yeah. Okay then. So we'll meet you tomorrow again. So okay. Bye then. Yeah.
Thank you.
Thank you, sir.
Hello.